Welcome everyone to this webinar on advanced sample preparation by broad AMB milling for EBSD analysis by Bruker and Fischione. So thank you for joining us today. I'm Laurie Pallas, Senior Application Scientist at Bruker Nano Analytics here in Berlin. I will be the host and presenter for this webinar, together with Pavel Novakovsky, Application Scientist at Fischione Instruments in Pittsburgh.
Welcome everybody, my name is Pavel.
And today, Pavel and I will review the challenges and solutions of sample preparation for electron backscattered diffraction analysis. So before we start, I'll give you some housekeeping details. So you should now see the introductory slide on your screen. This webinar is interactive, so you can ask questions at any time in the according question and answer box on the right side of your screen. The presentation will last about 40 minutes, and we will then move on to the Q&A session. If we are not able to get to your questions during this live event, we will follow up with you by email. This webinar is being recorded and will be available very soon as on-demand version. So this presentation is divided in 4 parts. We will first start by reviewing the EBSD technique and Bruker, so EBSD detector and imaging system. Then Pavel will present Fischione sample preparation solution by broad AMB milling before presenting some stunning application examples. And we will end up with the Q&A session. So I will now introduce the EBSD technique for those of you who are not familiar with it. On the background is an image of our Bruker EBSD eFlash fast and sensitive detector. So what's EBSD? EBSD stands for electron backscatter diffraction. It's a scanning electron microscope-based technique that measures the absolute crystal orientation, absolute orientation of crystalline materials. It can resolve grain size as fine as, let's say, 300 nanometers for bulk samples and 10 nanometers grain size for electron transparent samples using transmission Kikuchi diffraction technique. Because it's SEM-based, it correlates the material texture with the microstructure, and therefore it's a complementary technique for XRD and TEM studies. EBSD contributes to the material analysis by measuring the grain matrix, orientation, and of course identify the phase distributed in the sample and their distribution. So for instance, it helps investigating phase transformation, failure, material strength. So it's an ideal complementary analytical technique to the chemical characterization of the samples by energy dispersive X-ray spectroscopy analysis. So how does it work? So here on the left is a schematic view of the EDS and EBSD setup in the SEM chamber with a sample tilted at 70 degrees. When the electron beam strikes the specimen, we have electron scattering in all directions below the sample surface. The electrons, which satisfy the Bragg condition to a lattice plane, are channeled as a diffraction cone or Kossel cone for each diffracting plane. Electrons are then converted to photons by the phospho screen, so giving the diffraction pattern, detected by CCD and CMOS camera and digitized. So each diffraction pattern is then analyzed by the Bruker EBSD software. The sample is tilted at 70 degrees to normal incidence of the electron beam to optimize the fraction of electrons scattered from the sample, so to get this good diffraction pattern, so with great contrast. It's important to note that the backscattered volume is very small, only the top few nanometers below the sample surface. That's why sample preparation is critical for EBSD analysis. The subsurface has to be free of deformation induced by the preparation. Here is an example of an EBSD phase map obtained on a duplex stainless steel specimen with austenite in blue and ferrite in green and their corresponding diffraction patterns. EBSD measurement is performed by scanning the sample using beam or stage movement. So for each point, we collect the EBSD and or EDS spectrum. The pattern is transformed into the half space to identify the diffraction band position and index a pattern by comparing it with a database of more than 300,000 phase files. Phase and orientation are determined for each point. Thus, as we move the beam, we map the sample, characterizing the intragranular deformation, different grains, and phases. In this stainless steel example, phase identification would not have been possible using the chemical information only. EBSD is required to distinguish ferrite from austenites. So from one single EBSD measurement, we retrieve a lot of information: phase distribution, orientation, so the texture, grain matrix, strain localization, and so on. Here is the distribution of the phase and grain boundaries, as well as the CSL sigma 3 boundaries detected in this measured area with the total length. The biggest advantage of the EBSD analysis is that it's the only technique that correlates the local texture with the microstructure. So this is the grain distribution map in random colors. So benefiting from this large field of view of the SEM, EBSD provides quantitative data in a timely manner. In this example, more than 5,600 grains were measured in 30 minutes. The grain detections and grain matrix data were calculated in only 2-3 seconds. So here the average grain size is 11 micron. Many other applications of EBSD exist. Most importantly will be TKD, or transmission equity diffraction. It's an EBSD-like measurement at the nanoscale resolution by measuring an electron transplant sample using the EBSD hardware, so in the SEM. We also have, of course, SEM in situ experimental studies with high temperature or mechanical testing, for instance, and EBSD and EDS measurement in 3 dimensions by combining EBSD and EDS with serial sectioning, such as focus ion beam milling, for instance. But today we will focus on EBSD. And it's important to remind you that because the backscatter diffraction volume is very small, only a few nanometers below the sample surface, a good sample preparation is critical for EBSD. We will demonstrate that the combination of fission, broad ion beam milling with the EBSD, with the Bruker EBSD system, provides solutions to achieve not only excellent sample preparation, but quickly assess its quality using the Argus imaging system and reveal any artifact induced by the milling preparation on the EBSD orientation map or misorientation map. As you can see here, this is a single grain of copper that was plastically deformed. The lattice strain is visualized on the Argus orientation image by the change of color and also detected in the orientation distribution map and calculated in the misorientation map. So what is Argus? Argus is our built-in imaging system for EBSD and TKD detector to capture orientation and atomic contrast images. And I will now explain how it works and why it's essential to EBSD analysis. Imaging the surface of a highly tilted sample with traditional secondary electron imaging or backscattered electron imaging is difficult. For instance, this is stainless steel, so an SE image of a well-polished stainless steel sample, and we cannot see the microstructure, except contamination from some EBSD test map. You cannot see anything. And to alleviate this challenge, EBSD detectors have silicon diodes mounted below the photo screen to capture orientation contrast images, or FSEs, like this one, for instance. So as you can see here, FSE imaging achieves high intensity and high contrast orientation image of the tilted sample surface. The microstructure of the stainless steel is revealed. But black and white images using 1 or 2 FSE diodes is not always enough. If you look, for instance, at these grains here, there, and there, you will see that the substructure is only possible using 3 diodes using color-coded FSE images. So this is now the color-coded image. So these grains, for instance, if I go back, you don't see the twin boundaries inside. So with Argus, the operator evaluates the sample preparation quality with only a few seconds and can easily find the region of interest and look at the distribution of plastic strain. This unmatched sensitivity is because it's a direct electron detection system, fully built in the EBSD detector, so you don't get noise. And the speed of the image is up to 125,000 points a second. So Argus is a direct electron detection imaging system composed of 2 silicon diodes above the phosphor screen to capture backscattered electrons for atomic contrast images, and 3 silicon diodes below the screen to capture backscattered electrons with forward directions, named FSEs, to image the orientation and topography contrast. Each FSE diode receive a similar amount of noise, but a different signal or electron count for each pixel in the scanned area. So each diode has a separate channel. So when scanning, each pixel will obtain 3 numbers, which will be transformed into 3 RGB levels. And then when we mix the RGB levels, we obtain colorful images, like, for instance, this one. This one looks a bit funny. It's an example on stainless steel again. Here the area is scanned using the 3 FSE diodes only. The top of the image shows high contrast because it corresponds to the bottom of the sample, which is closer to the FSE diodes, as opposed to the lower part of the image, which is closer to the pole piece, further away from the FSE diodes. So why we have this distribution of color? Because this is the raw FSE image captured at low magnification. And at low magnification, the beam deflection is clearly noticeable on the FSE image. So you see different signal captured by the diodes, and this is automatically corrected by the Esprit software, resulting in such a stunning color-coded orientation image. And yes, like I said, you can assess the sample preparation quality in only a few seconds with the speed up to 125,000 points per second. You can adjust the scanning step size, so to resolve the finer substructure, making sure there is no astigmatism, the focus is good, and for both EBSD and TKD technique. So the rule to keep in mind is that if the Argus image is good, so will be the EBSD measurement. And this is another example on a strongly plastically deformed tantalum, where we clearly distinguish the intergranular deformation with this change in color within a grain due to the lattice rotation accommodating the plastic strain. And because it's a direct electron detection, Argus can detect orientation changes below 0.1 degrees. So for instance, here there is actually a subgrain. And it provides the orientation contrast images with highest resolution, ideal for your presentation or to qualitatively investigate plastic strain and residual stress. But for this, sample preparation is the key, since the subsurface must be free from deformation induced by the preparation. And now we will see with Pavel how the EBSD sample preparation can be optimized.
So in that part of presentation, I will cover broad ion beam milling and introduce you to our model 1061 SEM Mill. As you can see here on that picture, is the tabletop instrument that is most versatile broad ion beam mill for SEM application. It can produce the planar and cross-section artifact-free samples. Is it easy to use, fully automated, has liquid nitrogen stage cooling and vacuum inert gas transfer to SEM capability in order if you want to process environmental sensitive samples like lithium batteries, for instance. We have two milling geometry. One is planar and cross-section milling, as you can see here on that pictures. In case of planar milling, the sample is affixed to standard SEM holder and the top surface of the sample is polished. In the case of cross-section milling, the sample is affixed behind the mask, protective mask, and this is very critical if you want to preserve the edge of your sample or prepare this multi-layer specimen. This milling angle can vary from 0 to 10 degrees, and the milling angle is the angle between sample surface and ion beam. The stage can continuously rotate on rocked. So how it works, the argon ions strike the sample surface, removing atomic layer band layer, and in case in cross-section, everything which is above the mask, which will be removed, leaving flat surface showing your native microstructure of your material. Here we can see the cross-section of our model 1061 SEM Mill. You can nicely see two ion sources, two Faraday cups that allow you to monitor the beam currents, the stage and the sample, the load lock area and chamber area. Now the stage and the sample are in load lock area. In the next slide, the sample and the stage are in chamber, in the milling position, ready to be milled. The very important feature of our system is automatic sample high laser detection. As you can see here, it means the laser detects the sample high and the sample is automatically put in the right milling position, so no alignment is needed by the user. On the next slide, you can see the sample in the cross-section geometry position. As you can see, we don't change any stages between planar and cross-section milling. Only the way how the sample is sitting on the standard SEM holder changes. You can see here, you can see the protective mask and the sample is affixed behind in the milling position ready to be milled. So there is also no transformation between preparation and observation. We use the standard SEM holders that fit any SEM, and after your sample preparation, you can go directly to SEM for EBSD measurements. The model 1061 SEM Mill is dotted by true focus ion sources. We can deliver the energy, ion energy from 100 eV to 10 kiloelectronvolts. So you can see here on that picture, it is very easy to change the beam size using the parameter, focus parameter from interface, as you can see here, keeping the consistent current. So what the broad ion binning does, as you know, the sample preparation and surface conditions are critical for EBSD measurement. If you mechanical polish your sample, you will get a lot of scratches and damage on the surface, as you can see here on that picture. After ion binning, the scratches will be removed, all mechanical damage from the surface will be removed also, and you will expose your native structure on the material ready to be measured by EBSD. So now I will move to the application examples, and the first will be austenitic steel. The austenitic steel sounds easy, but can be very tricky for sample preparation. As you can see here, or the orientation contrast image collected with Argus system, we can see austenitic sample polish mechanically using colloidal silica. You can nicely see the microstructure of the grains distribution, but if you look closer, you can see that there is something happens here. Some different phases maybe is present. So if you look closer, zoom in, you will see that indeed there is some grains has changed very fine microstructure, and the surrounded grains are different. If you measure those structure using EBSD, you will find that this fine structure is the martensite and surrounded structure is austenite. This is a result of dynamic strain induced phase transformations of austenite to martensite during mechanical polishing. So if you map such sample using EBSD, you will get some fraction of martensite here showing in pink color, and the remaining fraction of austenite here showing in light blue. So as you can imagine, there is no martensite in that sample. It's only the product of dynamic strain-induced phase transformation on the surface. So this is very important if you want to study the sample. The steel sample will contain retained austenite. If you polish such sample using mechanical polishing, your retained austenite will transfer dynamically to the martensite, and you will not be able to measure it anymore. So it is very important the accurate sample preparation. If you use argon ion milling and our model 1061 sample preparation system, you will get 100% of your native structure and very clean sample. As you can see here, we observe 100% of austenite and no dynamic phase transformation is observed.
And if we look at the orientation distribution in 2 dimensions with this stereographic projection or pole figures, we can see that the austenite grains have the same orientation for both sample preparation technique. And if we look at the orientation of the martensitic grains here on the left, we can identify common poles with the austenite orientation. This is a diffusion-less dynamic phase transformation from austenite to martensite, which occurs according to a fixed crystallographic orientation relationship, described here. The observed orientation relationship seen in the pole figure is a direct consequence of the atom movements that occur during the transformation in the solid state.
So yes, and even if you zoom a conduct high-resolution EBSD measurement, you will find no dynamic transformation in the case of argon ion milling samples, and you will nicely see the martensitic structure after mechanical polishing, as you can see here on that IPF maps, and the clean 100% and the austenitic structure in the case of the ion milling samples.
And another way to test sample preparation quality is to use the kernel average misorientation maps. So the CAM shows the average orientation change or misorientation between each pixels and its neighbors. We are typically using a kernel size of 3 by 3 pixels using 5 degrees as threshold angle, and for any CAM map that you will see in this presentation. The CAM reveals the local misorientation changes, so subgrain boundaries and the local plastic strain. If the sample was poorly prepared, we would see the misorientation along scratches, or for instance, here on the left, we can see that martensite contains a lot of dislocations as compared to austenite. And on the right, we can see that there is no deformation induced by the broad AND milling preparation. And now let's look at a very difficult material. And there was an example in the webinar invitation. It's the zirconium alloy, but as you have never seen it.
Yes, zirconium alloys are very difficult for sample preparation. As you can see here on the next slide, on the left, there is example of zirconium 702 alloy, which was heavily deformed. On the picture on the left, you can see the mechanical polish sample. No microstructure is visible. Only some topography from mechanical polishing. This is because the zirconium is a ductile material with hexagonal structure with damage very easily during mechanical polishing, forming the thin top surface layer that is very difficult to remove. But in case of argon ion milling, as you can see on the picture on the right, you can see the fine microstructure is revealed. So you can distinguish nicely the formed structure as some biggest grains here. Of course, you can map, you can check both sample if they produce any EBSD pattern. So if you really carefully and long enough polish zirconium sample by colloidal silica, you will find maybe very few, very poor quality patterns, as you can see here on the left. But using argon ion milling, you will get beautiful, excellent quality pattern, very sharp everywhere, that allow you to get measurements with the indexing rate close to 99%. As you can see here on the pattern quality EBSD map, you can easily distinguish the small grains, all the microstructure, the bigger grains. You can look at the EBSD IPF maps. As you can see here, this map is just beautiful. You can see nicely smooth color changes within the grain that show you the lattice rotation due to deformation accommodation by crystal. You can distinguish some small grains over here, and bigger here, and once again the smaller here and here, that has a constant color. And in that particular, you can look at the grain average misorientation. This representation will show you in the blue color the less deformed on the recrystallized grain, and in the red color the most deformed grain, following this rainbow misorientation scale over here. And from that histogram you can easily create the subset of recrystallized grains with the misorientation angle from 0.01 to 0.6 degrees, which is showing in the blue in that map. Of course, you can look also at the kernel average misorientation here, and you will see that no artifact is observed after ion milling. You can easily visualize the low angle boundaries on the area with high concentration of dislocations.
And now let's look at another sample, commercially commercial pure titanium. So make sure I have the pointer. Yes, works. So this sample was polished with the Fischione 1061, but over a large area, as you can see here on this Argus orientation contrast image with 1 micron pixel size. So if we zoom in, we can see that we have a very fine structure. Now we are using a pixel size of 300 nano. And as you can see, it looks quite promising for the EBSD measurement. The phase was identified using combined EDS and EBSD in a single measurement. As you can see on the right, the diffraction pattern is of great quality. So it's pure titanium, so ACP hexagonal titanium. So we proceed to a large area EBSD mapping, combining automatic stage and beam movements to cover an area of 7 by 3 millimeter, using a step size of 1 micron. And the indexing rate was 99%, and it was achieved everywhere on this large area. If we zoom in, using a step size of 500 nano, we can see that the measurement is free of deformation induced by the milling preparation. In this single measurement, more than 121,000 grains were measured, with an average grain size of 23.5 micron. Now we'll look at another example on titanium alloy this time. As you can see on the Argus image, the microstructure is much finer than in the previous example. We are using a pixel size of 50 nanometers. And on this image, you can already distinguish two phases, one with larger grains and one with finer grains. This titanium alloy contains indeed two phases, alpha titanium phases, which is hexagonal ACP, like the previous one, and beta titanium phase, which is cubic PCC. The quality of the diffraction patterns proved that both phases were well polished, and both phases were again identified using combined EDS EBSD measurement. And note that the phase identification can be done before the measurement or any time afterwards without requiring the microscope, just by using saved EDS and EBSD data, and you don't need to save the pattern. So you don't need to produce a very large data set. This is the resulting EBSD measurement, so the phase map with an indexing rate of 98%, and you can see the fine cubic titanium phase in red. And the spatial resolution is achieved, it's 60 nanometers resolution. And if you are curious, this is the corresponding orientation distribution, showing an orientation relationship between the HCP alpha, so 110, it's the equivalent of a 11 minus 20, with the 111 direction of the cubic beta phase. And now we will proceed to one last challenging example with Pavel on solder bumps.
So yes, the solder bumps are very challenging materials for sample preparation. This is because they are part of the semiconductor devices, and they are made basically from copper and tin alloys. As you can see here, both materials are very soft and has very fragile structure. So if you attempt to polish mechanically solder bump sample, you will get the result like here. So there is a lot of different issues that you can observe on that images. The main issue is the differential of material removal between tin and copper. The tin remove faster than copper, so the copper will be higher in your sample, shadowing the interface would be not accessible by EBSD measurements, as you can see here. And interface is critical for failure analysis. Also, don't forget that silica particles are very difficult to remove from the surface after mechanical polishing. You have to use different liquids to remove them and some mechanical action to remove them from the surface. And even your gentle finger can damage and destroy your nice preparation. And also, these liquids can react with surrounding package components, and the corrosion product can contaminate the surface, as you can see here and over here. So the results of the mechanical polishing will be disaster like shown here. So what is the best way to prepare solder bumps cross-section? The best way to prepare solder cross-section is the using model 1061 with the cross-section configuration using the mask under the milling condition. You can produce the nice cross-section up to 2 millimeter width with the several solder bumps cut nicely in the half, as you can see here on that images. You can zoom in on any solder bumps and starting your structural and failure analysis. As you can see here, you can distinguish nicely. There is some secondary phases in the solder and some interface formation at between a solder and the copper pad. So of course, using EBSD technique, using such good sample preparation, you can identify all the intermetallic phases, as you can see here, and of course map whole solder bump with the copper pad. As you can see here, you can nicely see here the phase distribution of intermetallics in the solder bumps and the interface between copper. You can calculate the fraction of each phases. You can easily calculate the average grain size for each phases. Of course, having the EBSD data, they give you access to many of information, like you can look at the orientation IPF maps. Once you have the orientation, you can easily look at the kernel average misorientation, which show you very local changes of the orientation in your sample, in your structure, and then you can easily localize the strain accumulation of your sample that can indicate you when the failure of your solder junction can happen during device lifetime. Of course, you can make conduct high resolution observations. As you can see here, this is excellent colorful Argus image on the interface of our solder bumps. As you can distinguish here, the solder bump structure, the copper pad structure. You can see the distribution of fine intermetallics particle in the bump and at the interface. Of course, this area you can easily map using EBSD system and get beautiful maps as here and start your advanced structural and failure analysis. So with that example, we'll finish our application presentation. I will move to the summary of the webinar.
Thank you, Pavel, for this great presentation. Yes, so to summarize this presentation, we would like to highlight that combining Fischione sample preparation solutions with Bruker EBSD system is a powerful combination for SEM operators to quantitatively characterize the microstructure and texture of challenging crystalline materials. Both the sample preparation and EBSD measurement are done in a timely manner, achieving high angular and spatial resolutions even over a large area.
Yeah, the Fischione Instruments provides fast and reliable sample preparation solution for a wide range of applications and a wide range of challenging materials such as thermally sensitive samples like solder bombs and environmental sensitive samples like lithium-ion batteries.
And last but not least, the unmatched sensitivity and speed of the Argus imaging system allows qualitative mapping of plastic strain and even residual stress, since it detects orientation changes way below 0.1 degrees, completing the EBSD system into an ideal analytical tool for deformation studies. So we will now have our Q&A session that will last 15 minutes or a bit more. So first, a quick reminder to our viewers: you can submit a question by entering it into the according Q&A field on the right side on your screen and press submit. We have already a number of questions and a lot of questions for you, Pavel. So I will start by the EBSD questions, so you have time to look at the many questions. So we won't have time to review all the questions, I doubt, but if we don't answer your question today, we will answer it by email. So I'll start with EBSD question. Can we use mechanical polishing to prepare samples for EBSD analysis? So yes, for many of them, but like Pavel has shown you at the beginning of this presentation, you have to be very careful. So soft materials cannot be prepared, and materials with phases with different hardness and very fine microstructure cannot be prepared by mechanical polishing alone. And those will require broad ion beam milling. Another question someone asked if, let me try to find it back. Which software, what is the software? Oops. What is the software that we have used for the misorientation of the grain? So I think you referred to the kernel average misorientation maps. Let me go back to one example, maybe the austenite ones. So we are using one single software, Esprit, to acquire the Argus images, acquire the combined EDS EBSD measurement, and calculate the misorientation map. So this kernel average misorientation map, and also you've seen like this grain average misorientation map. Pavel, maybe you want to start by. Yes, go on.
Yeah, I have a nice question I would like to answer related to the presentation. So the question is, how long has the austenite samples been ion milled, and what angle would you recommend it for lead-free solders? So to answer the first question, I would say that all the results that you can see here and all the materials, you can get exactly the same result of sample preparation and EBSD measurement if you mill less than 1 hour. And the second question was what angle you would recommend it for lead-free solder. So I would recommend that 2 or 3 milling angles. 2 or 3 degrees, sorry, 2 or 3 degrees milling angle.
Okay, do you want to answer another question, or should I ask the EBSD one?
Ask one EBSD. And
yes? Okay, because you have a lot of questions. So, yes, is it possible to measure a non-conductive sample with EBSD? So yes, you can use the either SEM low vacuum mode for the measurement or apply a thin carbon coat on the sample surface. But if the sample is well polished, like you've seen in the solder bumps examples, you can do the measurement just using high vacuum but lower voltage, and there will be and then you can do a fast EBSD measurement without anything else. And porosity is also not a problem. So you saw this nice results on the solder bumps, but also you'll have the same for the ceramics.
So I have one related a little bit to conductivity question here. So can we use the FIB to prepare the oxide materials for EBSD, such as electron materials used in batteries? Does they need additional treatment to make them electrical conductivity? Thank you. So here we use the broad argon ion milling, which is a little bit for the different than FIB, but of course using the model 1061 and broad beam ion milling, you can prepare such sample like oxide materials and electrode materials used in batteries. We do a lot of batteries in our application lab. There is no reason that you cannot prepare them using our milling system. And does they need additional treatment to make them electrical conductivity? Yes and no. If you do the cross-section, you will affix the sample to the protective mask. So in that way, you will ground your sample, because if you want to prepare non-conductive sample, the only issue could be that you will have ground somehow in your milling target area. If not, there is no problem at all preparing non-conductive samples.
Thank you, Pavel. I see that there are a few questions about the two different KV settings, and the fact that we often actually use the similar recipes, which is very convenient. I don't know if you want to talk about it. There's many questions, so maybe it's difficult for you to see them all.
Yes. So we usually mill at some KV like 10, 8, or 6, and then we do clean up at low KV, which could be 2 on 1 kiloelectronvolts. So if you look at that example, we remove basically the damage and scratches from the sample. This is cross-section, so there is not scratches, because this is a cross-section sample. So in case of cross-section sample, the solder bombs are never polished mechanically. The sample, if you detect the row that have defect, you want to investigate it, you cut the sample before the solder bombs. The solder bombs is never affected mechanically. Then you align your mask in the center on the solder bomb and just remove what is above. So you get beautiful cross-section in the center of the solder bomb for failure analysis. So we use 6 kV to remove all that material, which can be a lot of material. We can imagine this cross-section has almost what they have about 300 microns. So you can imagine there's 300 microns of the material above the mask, plus some material of the package, which is before the bomb. So you have to remove all of that, and then with 2 kV we just clean the area, and 2 kV is very short, like minutes milling. So it's only high energy for material removal and low energy for fast surface cleaning.
Thank you, Pavel. Someone is asking if we have good quality pattern with samples prepared by FIB for conventional EBSD technique. So yes, I mean, we test anyway when we do 3D or so. You could use the focus ion beam milling to prepare the area for EBSD. Of course, it's possible. So I guess yeah, you were talking about.
If I can add something to that question.
Please.
Yes. So of course, using the FIB, you will get very restricted area.
Yes, so, even for plasma FIB,
yeah,
it's a little bit restricted.
Even for plasma FIB, you will not get more than 100 microns width area, which is very small. Using broad beam argon ion milling, you can get for the model 1061 up to 10 millimeters in diameter area. And of course, we have the solution also. If you need more, we can go up to 50 millimeters diameter of area of milling. So you can achieve the huge milling area comparing to the FIB. It will be very small.
Someone is asking, do you remember the total duration for the complete cross section of the solder bumps?
I will have to look at it and
so the 2 kV step was few minutes, huh? Right? I think you mentioned it before.
Yes, it's right. It's right. It's few minutes. Always the cleaning step is few minutes.
Okay. Yeah. My pointer is gone. Okay. Yes. I don't know if you want to ask another question.
So there is nice question about why is argon chosen over gallium. Argon damage less the material, and we don't have the implantation on amorphization layer on the using argon. Like we use gallium, you get the implantation layer of gallium, and amorphization on the top of the surface. Using the argon, we don't have that effect. And we also, in Fischione Instrument, there's a gamut of instruments for TEM sample preparation. They all use argon beam for sample preparation. In just those instruments remove the gallium damage from TEM prepared lamella. So that's why we choose the argon over gallium. Create less damage to the material than gallium.
Thank you, Pavel. Yeah, there are more questions for you. Let me know if I should go on with any EBSD question in case, to give you time to read all the questions.
Yeah, go with EBSD question.
I have a TKD related one. So someone is asking if how we prepare samples for TKD measurements. So ion milling is the best technique, of course, for polishing very fine microstructure. And yeah, you use TKD when the grains are finer than 300 nanometers. So actually, the example here on we are close to the limit of the EBSD box sample. So for the very fine grains. Yeah, for TKD, you need an electron transparent sample with maximum 3 layers of grains to achieve so up to 2 nanometers or down to 2 nanometers spatial resolution. But that means that the feed preparation is challenging because you need maximum 2-3 layers of grains. So you might need to have a lamella of 20 or 30 nanometers in thickness. So if this is too challenging for your FIB, you could also use the Fischione nanomill to reduce the sample thickness and also clean from the gallium implementation. Pavel, do you want to go on with a question?
At least you want one more?
I don't know. Go on. Select the one you...
Okay. So we have one question. Do you have any recommendation from an additively manufactured 4340 material BMD process? I believe I'm having issue with carbides coming out and scratching the surface while mechanically finishing the sample. Yes, of course, the solution will be argon ion milling with the shallow angle, 2-3 degrees, and you will get beautiful results. And this is the common problem. If you have the soft matrix and hard particles dispersed inside, during mechanical polishing, they will go out and act like the abrasive and scratch your surface. So this is now the way to prepare the sample. The mechanical polishing will be not good. I would recommend it broad argon ion milling with the shallow angle. Lori, do you have a question?
Yes. No. So yeah, we'll have also. If there are more questions we have missed, we can answer them by email. If that's okay for you, Pavel?
Yes.
Yeah. Okay. So thank you very much for your time today. We conclude our Q&A session for this web seminar, but we will answer the remaining questions by email. So as a reminder, today's event has been recorded and will be available for viewing very soon. So thank you for being with us today, and we hope to have you with us again at future webinars. Goodbye.
Thank you. Goodbye.